Hello everyone and welcome to this short tutorial. In this session, I will walk you through a complete workflow covering training curve of visualization, confusion matrix analysis, random forest classification, model saving and loading, and finally vision transformers, VIT, and cross-validation techniques. By the end of this video, I hope you will have a clearer understanding of these essential machine learning components. Visualizing training curves. After training a deep learning model, such as CNNs, we typically extract several key metrics from the history object, including training accuracy and validation accuracy, training loss and validation loss. These metrics are plotted against epochs to visualize the model's learning progress. Why do we plot training curves? By examining the accuracy and loss curves, we can diagnose training issues. Overfitting. If training accuracy is high but validation accuracy stops improving or declines, the model may be memorizing training data rather than generalizing. Underfitting. If accuracy remains low and loss does not decrease, the model may need further training or tuning. These insights help us adjust hyperparameters, apply early stopping classes, or modify the learning rate. Part 2, generating a confusion matrix. Once we train our model, we make predictions on the test set and compare them with the actual labels using a confusion matrix. This allows us to evaluate the model's classification performance in more detail. How does a confusion matrix help? Let's say 0 represents sea ice, 1 represents leads. The confusion matrix will tell us how many actual sea ice pixels were misclassified as leads, how many actual leads were misclassified as sea ice. Visualization. Using confusion matrix display, we can create a blue-colored grid where each cell represents the number of correct and incorrect classifications. This visualization helps pinpoint which class the model struggles with the most, guiding further improvements. Part 3, random forest classification. Besides deep learning, we can also use random forest, a powerful traditional machine learning algorithm, especially for structured data. Basic workflow. 1. Initialize a random forest classifier, specifying the number of decision trees and estimators. 2. Reshape data. Since random forest expects input in the form of samples, feature dimensions, we flatten image patches into 1D feature vectors. 3. Train the model. The algorithm constructs multiple decision trees and combines their outputs for final classification. 4. Prediction and evaluation. We test the trained model on unseen data and use confusion matrices and accuracy scores to assess performance. Advantages of random forest. Faster training compared to deep learning models. Fewer hyperparameters, making tuning more straightforward. Performs well on smaller datasets or when convolutional architectures are unnecessary. Part 4, saving and loading models. Once we train a model, whether a random forest or CNN, we may want to save it for later use instead of retraining from scratch. Why save a model? Saves time. Avoids the need for length file for traditional ML models or use TensorFlow Keras formats for deep learning models. Part V, vision transformers. A newer approach to image classification is vision transformers. Unlike CNNs, VITs do not rely on convolutional operations. Instead, AI-based model training, evaluation, and vision transformers, a comprehensive guide. Hello everyone, and welcome to this short tutorial. In this session, I will walk you through a complete workflow covering training curve